All right, let's dive into a real cosmic whodunit. We're going on the hunt for the source of the most powerful particles in our galaxy. And you know what? The clues are hidden in the chaotic, magnetic wreckage of exploded stars. So, let's start the investigation.
So this is the big one, the question that's been bugging astronomers for decades. I mean, we know our galaxy is just buzzing with these incredibly powerful particles, but figuring out where they get all that juice from, well, that's been a massive challenge. Turns out the answer is hidden at the scene of some of the most violent events in the entire universe.
And here it is. This is our primary crime scene, a supernova remnant. What you're looking at is Cassiopeia A. It's what's left over after a huge star blew itself to bits about 350 years ago. These remnants, they're the prime suspects for being the galaxy's own particle accelerators. Basically, cosmic engines that crank matter up to unbelievable speeds.
To solve this thing, we have to think like real detectives. We need to comb through the evidence that's been left behind, and we're hunting for the fingerprints of this powerful, invisible force that's been hiding in plain sight for centuries.
Now, the mystery revolves around these things called cosmic rays. And don't let the name fool you, these aren't rays of light. Nope, they're actual particles, mostly protons and atomic nuclei, and they are zipping through space at pretty much the speed of light. They hit Earth all the time, but where they come from, well, that's been a puzzle for a long, long time.
So how in the world does a star exploding create these cosmic bullets? Well, the leading theory says it's all down to this invisible process that happens right at the edge of the explosion's shockwave. It's got this kind of clunky name, diffusive shock acceleration, or DSA for short. But forget the name. The best way to picture it is like a giant cosmic pinball machine. The shockwave from the supernova is like a flipper, and it just keeps smacking particles over and over, giving them a bigger energy boost with every single hit. So here's how this crazy cosmic pinball game works. First, a particle drifts across the shockwave. Then, bam! It hits this tangled mess of magnetic fields and gets shot right back. As it crosses that shockwave again, it gets another massive jolt of energy. Now imagine that happening thousands, maybe millions of times. Each pass gives it more and more speed, until it's flying at nearly the speed of light.
But, and this is a huge but, there's a catch. For that whole pinball machine to work, the particles can't just fly away after one hit, right? Something has to keep them trapped near the shockwave so they can get hit again and again. And that something, that invisible trap, is magnetic turbulence, a completely chaotic, tangled web of magnetic fields. And until just recently, we had no way to actually see it.
So to see something that's basically invisible, we needed a completely new kind of detective, something that could look at the universe in a way that we have just never been able to before. And in late 2021, that detective finally arrived on the scene. It's called the Imaging X-ray Polarimetry Explorer, or IXP. It's a space telescope, but with a really unique superpower. It can measure the polarization of X-rays, and that gives us a direct map of the magnetic fields right where these particles are getting supercharged.
And this, right here, is why IXP is such a game changer. You see, before IXP, our radio telescopes could kind of see the magnetic fields, but they were looking at the glow from older, lower-energy electrons. It was like showing up to a crime scene days late. But IXP sees the X-rays from the freshly accelerated highest-energy electrons. It's like having a high-speed camera filming the action as it happens.
Okay, so with IXP on the case, we could finally start dusting for those magnetic fingerprints, and the evidence it uncovered is fascinating. Let's take a look.
So first suspect up, our old friend, Cassiopeia A. IXP took a good long look and found that, yep, the magnetic field was mostly a chaotic, turbulent mess, just like the theory predicted. But it also found something we totally did not expect. Little pockets where the magnetic field was shockingly organized and neat.
And get this, in some of those tiny pockets, the degree of polarization was as high as 26%. I mean, that is a huge level of order hidden inside all that chaos. It was our first big clue that this whole magnetic field picture was way more complicated than we thought. All right, next on the list, Tycho's supernova remnant from back in 1572. And here, IXP found a much cleaner picture. The magnetic field was mostly radial, basically pointing outwards from the center like the spokes on a bicycle wheel. This is exactly the kind of signature we expected to see in a young remnant. But this is where things get really interesting. Take a look at SN 1006. It's like a tale of two different crime scenes in one. On the left, you see the northeast side, where the magnetic field looks all uniform and tidy.
But then you look at the right, the southwest side, and it's a total mess, highly variable. What does that tell us? It shows that the local neighborhood, in this case a dense cloud of gas, can completely change the magnetic evidence.
And then, IXPE looked at a couple of much older remnants, RxJ1713 and Vela Jr. And boom, a completely different pattern. Instead of those radial spokes we saw in the younger guys, their magnetic fields were tangential. They were wrapping around the shell, kind of like the stripes on a basketball. And this was a massive clue. A clear pattern was starting to emerge based on age.
So let's lay out the evidence, detective style. If you look at this case file, a pattern just jumps out at you. The younger remnants, Cas-A, Tycho, SN1006, they all show these largely radial magnetic fields. But as you get to the older ones, like RxJ1713 and Vela Jr., the whole thing flips. The orientation becomes tangential. It looks like the entire magnetic structure evolves as these things get older.
So, case closed, right? Our new detective solved it? Well, not exactly. In fact, like any good detective story, the new evidence has just made the mystery even deeper.
Okay, so let's recap what we've actually learned. What are the big takeaways? 1. Magnetic turbulence is absolutely essential. 2. The environment around the explosion dramatically changes the magnetic field. 3. The structure seems to change from radial to tangential over time. And 4. The simple picture we started with, it's gone. The reality is so much more complicated and honestly, way more fascinating.
And this quote from the researchers really nails the new puzzle. What it's saying is that in these older remnants, the part of the field that wraps around the shell is organized, but the part pointing outward is still a turbulent mess. So you can have order, which gives you high polarization, and chaos, which gives you particle acceleration, happening at the exact same time. How cool is that?
And just when you think you're starting to get a handle on it, the plot thickens. There's this wild new idea on the table called jitter radiation. It suggests that the X-rays we're seeing might not be from electrons just spiraling nicely in a magnetic field. No, the idea is that the X-ray light itself could be a direct signature of the turbulence, with the electrons literally jittering as they fly through the chaos. It's a whole new way of reading the evidence.
And that's really where we are right now, standing on the edge of a huge discovery. For the first time ever, we have the tools to see the invisible magnetic chaos that powers our galaxy. But as our cosmic detective, IXP, keeps gathering more clues, the big question remains. Are these magnetic fingerprints finally going to crack the case? Or are they just leading us down a rabbit hole to an even deeper, more complex mystery?